We are going to look at electric field in today's class. We all have heard about electric field. So today we are going to throw more light on it with some calculations. So an electric field is the region around a charged object where it can pull or push them without touching them. Remember, electric field is a non-contact force. So electric field is that region around a charged object where it can pull or push them without touching them. We can as well say that an electric field is the force F per unit charge experienced by a small test charge placed near another charge. Now, let's look at that mathematically. Then we can see that electric field E equals force F per unit charge. Let's call this equation 1. Now, let's say we have a big Q. Let's say we have a big Q. And this big Q is positively charged. And we want to calculate the electric field at some point. Let's say that point here, point A. And at this point A, we place a positive test charge, that is small q, at this point A. The distance between this big Q and the test charge is R. You know that since they are like poles, positive, positive, they are going to repel each other in this direction. They are going to repel each other in this direction. But the electric field will go this way from the big charge towards the test charge. This is the electric field. Now, according to coulombs, that F equals K, the big Q, multiplied by the small q, divided by R squared. So we can call this equation 2. Now, putting equation 2 in equation 1, we will now have that E, which is the electric field, will now be equals to, instead of writing F, we write K, big Q, small q over R squared divided by small q. So which will give us this small q, we cancel this small q, that's the test charge. So we will now be left with K Q over R squared. This becomes our equation 3. That is another formula for electric field. Now, let's go ahead and define the parameters used in equation 1 and equation 3. Okay, now we have the first one, the E. E is equals to electric field. electric field strength, electric field strength, and its unit is Newton per coulombs. We have another one there, F, which is force experienced by test charge, by the test charge. And the unit is Newton. We have another one, Q. Q is the test charge. Q is the test charge and it is measured in coulombs. Big Q is the source charge. The source charge creating the electric field. Creating the electric field. And it is measured in coulombs. R is the distance. R is the distance between the big Q, that's the big charge, and the point where the field is measured. Where the field is measured. And its unit is what? Is the meter. I hope you are okay with this. Okay, let's go ahead. Now, the first formula of electric field in equation 1, it tells us that electric field is the force per unit charge. Is the force per unit charge. While the third formula tells us how the field depend on the charge and distance. So we have the first formula, E equals F over Q. This is the first equation. Then we have E is equals to KQ over R squared. This is equation 2. So this first equation here, it tells us that electric field is the force per unit charge. Force per unit charge. While the second one tells us how the field depend on the charge and the distance. Okay. Now remember that electric field is a vector quantity. Electric field is what? Is a vector quantity. Electric field is a vector quantity. Is a vector quantity. It tells us how the electric force is going to be acting on a positive and a negative charge. So it tells us also how electric forces is going to be acting on a positive or negative charge. Let's take, for instance, we have an electric field here. Remember, we say that electric field is a region in space or around a charged object where it can pull or push them without touching them. So let's assume we have electric field at this point. Now, what happens when we put a positive test charge in this electric field? What will happen? Let's assume we have a positive test charge, a positive test charge. So what will happen when we place this positive test charge here in this electric field? What will happen? Okay, this positive test charge will experience a force that will accelerate it in the same direction as the electric field. So it's going to do what? Experience a force that is going to do what? Accelerate it in the same direction as the electric field. Is that understood? Please pay attention. I said this is electric field. We assume we have electric field at this point. We assume we have what? Electric field at this point. And we brought in a positive test charge, positive what? Test charge in this field. What will happen to this positive test charge? This positive charge test charge here is going to experience a force that will accelerate it in the same direction as this what? Electric field. What is the direction? They are moving what? In eastward direction. They are moving eastward, in eastward direction. Is that understood now? Okay. Now, let's assume we have a negative test charge in this field. Let's assume here now we now place a negative test charge in this field. What will happen to this negative test charge that we put in this electric field? What will happen? This negative test charge is going to experience a force that will accelerate it in the opposite direction to the electric field. So the direction of the force is going to be opposite to the direction of what? Of the electric field. This is very important and you have to take note of that. This is very important and you have to do what? Take note of that. We have this electric field here and we brought in a negative test charge here. This negative test charge is going to experience a force in opposite direction to that of what? To that of the electric field. Now, do you also know that charges can also create their own electric field? Do you know that charges itself, they can create their own electric field? Okay, let's take a look at this. Let's take a look at this. We have this positive charge. Now, this positive charge here is going to create its own electric field. So the electric field created by this positive charge will move radially away in all direction from the positive charge. That means it's going to move radially away. It's going to move what? Radially what? Away in all direction from the positive charge. And one good thing about this electric field that it is continuous. It keeps on going, it keeps on going, but as it's going out, it's reducing. The strength decreases. As it's going out, as it continues going, the strength does what? Reduces. the strength does what? Reduces, keeps on going. The strength reduces as it keeps on going. So this is for positive charge. This is for positive charge. So you see that the electric field move away in all direction from the positive charge. Okay, let's look at a negative charge. Let's assume we place this negative charge here at this point. What will be the direction of the electric field in this negative charge? So the electric field created by this negative charge will move radially towards this negative charge. It will move what? Radially towards this negative charge. So it's going to move inward in all direction. That is to say that it's going to come from here. It's going to move this way in all direction. It's going to move this way. So please take note of the arrow. So it's going to move towards the negative charge. It's going to move what? Radially towards the negative charge in all direction. This is the electric field. Electric field. This is the electric field. They are going to move towards the negative charge. Now, let us consider, two different charges. That is the plus and minus charge, positive or negative charge. And the field created by this positive and negative charge is what we call the dipole field. Dipole field. You must have heard about this before. Dipole field. Now, let's assume we have this. We have a positive charge here, and we have a negative charge here. So you see, the first field will move from top to bottom, from top to down, this way. You see the arrow? So it's moving out from the positive charge and entering inside what? The negative charge. Now, another one is going to come out from the positive charge this way, then enters towards what? The negative side. Another one will come out from the positive charge and enters what? The negative side. Now, you see, you may think that this will continue this way, like this. No. Physics is smooth. So, therefore, we are going to draw it lovely. Then it's going to be like this. We're going to draw a very good line, you see, to join it. So this is the direction. So this one also moves and enters. This is what? The direction. So another one will come out from positive charge and enters towards the negative charge. So we complete it. The arrow is very important. Please don't forget. So another one will come out from positive charge and enters towards the negative charge. So we're going to complete it. So it continues in that way. It continues in that way. It continues in that way. But one thing you have to note in this is, the first one is the strength of this electric field. The strength of this electric field has to do with the density of the lines. The density of what? Of these lines. That is where the strength lies. The density of the lines. If these lines are close together, the field is strong. If these lines are close together, the field is strong. But if these lines are far apart from each other, the field is very weak. Another thing you need to know is that these field lines here, they do not touch each other. You see, they will not do what? Touch each other. Another thing you need to note also here is that these field lines, that they emanate from the positive, and they do what? And they terminate, or they enter at the negative charge. So dipole fields are very important. This type of dipole field is very important because atoms are made up of positive charges and negative charges. We have what we call the polar molecules. Example of a polar molecule is water. Water will have a negative end and a positive end. So the field that surround them are dipole field. The field that surround them are called what? Dipole field. So these field lines, just like I earlier said, it originates from where? From the positive what? Charge. And it terminates here at the negative charge. So this positive charge here is what we call the source. Why this negative side here is what we call what? The sink of the electric field. The sink of the electric field. Okay, now let's take a look at a solid sphere of charge. Let's look at one solid sphere of charge. Now, let's think about the electric field from this solid sphere of charge. We have this. Okay, this is a sphere, and we have inside it filled with positive charges. Now, just like I said, let's put many positive charge inside this solid sphere. Now, what will be the electric field outside this solid sphere? What will be the electric field outside this solid sphere? What will be the electric field outside this solid sphere? So the electric field outside this solid sphere is going to extend outward in all direction. So it's going to do what? Extend outward like this in all direction. It's going to extend outward in all direction. In all direction. It's going to extend outward in all direction. Now, what about electric field inside this sphere? If it is uniformly what? Charged, what will be the electric field inside what? This sphere? If it is what? Uniformly charged. Okay, let's take a look at that. Take a look at that. This is the same solid sphere. Remember, this is exactly the same thing. So we are trying to look at the electric field inside the same solid sphere. Now here, this is the middle of this solid sphere. So at the center of this solid sphere, the electric field at this center is going to be zero. So the electric field at the middle or the center of this solid sphere is going to be what? Zero. Meanwhile, the electric field elsewhere in this solid field is not going to be equal to zero. So here, elsewhere is not going to be equal to zero. Now here, as soon as you go out from the center, the electric field also starts to do what? Go radially again outside. So immediately you move from this center, you will see that the electric field will do what? It will start to move radially away outside. It start to do what? Move radially away outside. I hope that is well taken. Okay, let's go ahead and look at a hollow shell of charge. A hollow shell of charge. Number two, we look at this hollow hollow shell of charge. Hollow shell of charge. Hollow shell of charge. Now, let's put charge all the way around the outside. So here we have this hollow shell. So let's put charge all the way around this hollow shell. Let's put a charge around it. Now, what do you think? What do you think the electric field will look like on the outside? Yes. What do you think that the electric field will look like outside this hollow shell of charge? Of course, it will point radially out from the shell. It will do what? Point radially what? Out. From what? From the shell. It will point radially out. It will point radially out from the shell. Now, what do you think will be the electric field inside this hollow shell? What do you now think will be the electric field inside this hollow shell of charge? Yes, what do you think will be the electric field inside the hollow shell? Now, here, it will be going away from the positive charge. This is the positive charge here. This is what the positive charge. These are the positive charges. So the electric field will be going away from it. It will do what? It will be going away from it. It will be going away from where? From the charge, from the source. It will be going away from the source. You understand that now? So here, a sphere of uniform charge has a electric field equal to zero elsewhere, anywhere inside this hollow shell. So here, the electric field inside this hollow shell of charge will be equals to 0. So here E is equals to what? 0. Where? Inside. Inside this hollow shell. Remember when we are talking about the solid sphere, the electric field is only equal to 0 at the center. That is the midpoint of what? Of the solid sphere. But in a hollow shell, inside the hollow shell, electric field is equals to 0. Is that understood? Okay, let's continue. Okay, let's say we have a positive charge. Let's say we have a positive charge here. Let me also explain this using this. We have a positive charge here. Okay, let's use a big Q. Let's say we have a positive charge here, Q. And we have point A, B, C, and D. Okay, we have this point. We can have this point here. Point A, we have this point. Point B, we have this point. Okay, we have this point. We can call it point C. And we have this point. We can call it a point D. Now, determine. How can we determine the electric field? How can we determine the electric field created by this charge at the point A, B, C, D? How can we determine that? Now here, the electric field will move from positive Q to point A. It's going to move from here, this positive Q, to point A. Where? To the north. Are you there with me? So this electric field is going to move from charge Q to D. So this in the what? Northeast direction. So it's also going to move from the charge to point C in the southeast direction. And it is also going to move to point B in the west direction. To the west direction. Okay. Now let us do similar thing to a negative charge. Please pay attention to the arrow. The arrow is very important because electric field is a vector quantity. So arrow head is very important. Okay, let's look at that of negative charge. Let's assume we have negative charge here and we have a point here, B. We have a point here. We can call it A. We have a point here. We can call it D. Then we have a point here. We can call it C. Now you will see that the electric field will point towards the negative charge. It's going to do what? Point towards the negative what? Charge. It's going to point, it's going to come from B. It's going to move down to this charge. And in what? In south direction. Of course, you know about your four cardinal points. This is the east. This is the west. This is the north. and this is what the south. So here, the electric field is going to move from B to the charge, that is southwards. Now, it's also going to move from A to what? To the charge. That is what? In the west direction. In the west. Remember, this is what? Electric field, E. Electric field, what? E. So it's going to move from D to the charge inwards. This is what? This is the electric what? Field. And that is what? North. In north direction. So it's also going to move from C to the charge. That is in east direction. That's your electric field. I hope that is well understood. Okay, now let's go ahead and play with some mathematical question. Let's go ahead and play with some mathematical question. Now, a positive test charge of 20 microcoulombs, of 20 microcoulombs, a positive test charge of 20 microcoulombs is placed in an electric field. Is placed in an electric field. The force on it is 0.5 Newton. What is the magnitude of the electric field at the location of the test charge? Now, the first thing we have to do, please pay attention, is to do what? Is to write out the parameters. Here, we have 20 microcoulombs. So this is what? Your charge Q. That's your charge Q. Now we have another one is what? The force on it is 0.5 Newton. So this is our force. This is the force. Then we are now asked to calculate what? The magnitude of the electric field. We are looking at what? The magnitude what? Of the electric what? Field, which is E. Now let's go and write out the parameters. So we have Q is equals to 20 microcoulombs, which you convert to coulombs by multiplying 20 times 10 raised to power negative 6 coulombs. This one is set. Then we have our force. That's another parameter, is the force, 0.5 Newton. Then the question asks us to calculate what? The electric what? Field. The magnitude of the electric field. Then we recall that electric field E is equals to force per unit charge. Remember from the definition. So we put in our values. Force equals 0.5 Newton. Then we do division. Divided by the charge Q is 20 times 10 raised to the power negative 6. So when we divide that, we are going to have 2.5 times 10 raised to power 4. Then this is what? Newton. This is division sign. And this is coulombs. So the answer becomes 2.5 times 10 raised to power 4 Newton per coulombs. I hope that is well taken. Hope that is well taken. Okay, let's quickly move into another example. A force of 100 Newton, a force, this is F, a force of 100 Newton is directed north on a negative 30 microcoulomb point charge, which is our Q, what will be the magnitude and direction of the electric field at this point? What will be what? The magnitude and direction of the electric field at this point. Okay, let's go ahead and try to illustrate this. Let's assume, like it says, that a force of 100 Newton is directed north on a charge. So we have what? This negative charge, Q. We have the negative charge here. And the value of this negative charge is, we know that the value is negative 30 microcoulombs. Now, it says that a force of 100 Newton is directed north on it. That means this is north. This is north. And this is the force. And it is directed towards north. And this force is 100 Newton. Now, it's asking us to calculate what? The magnitude and direction of the electric field at this point. First of all, let's look at the direction. Remember that this is a negative what? Charge. And we have been told that the force is directed towards north. So where will the electric field have its direction? The direction of the electric field is going to be what? In opposite direction. It's going to be what? In opposite what? Direction. So this will be the direction of what? Of the electric field. So it's going to be what? South. So remember, when I said something about what? Electric field and what? And a point charge. I said before that let's assume that we have electric field. This electric field is moving this way. Then when you bring a positive charge to it, so the force is going to move in the same direction with what? With the field. I hope you remember that. But when you bring a negative charge to it, it's going to do what? Move in the opposite what? Direction. So if you had paid attention earlier, you will get this right. You will get this right. I hope that is clear for you now. Okay. Now let's go ahead and calculate the magnitude of the electric field at this point. Now let us recall the formula for electric field. E is equals to F over Q. F over Q. Now here, what is our F? Our F is what? 100 Newton. Our charge is 30 times 10 to the power negative 6 coulombs, converting to coulombs. So we are going to have 3.3 times 10 raised to power 6 Newton per coulombs. So this becomes our answer. Okay, I hope that is well taken. Let's go ahead and play with question number 3. A positive charge of 50 microcoulombs. So this is our charge. This is our charge Q. Is placed in an electric field of 50,000 Newton per coulomb. So this is our E, directed upwards. What mass here should the charge have to remain suspended in air? So let's go ahead and write out our parameter. The first one is what? Is our charge, Q, which is equals to 50 microcoulombs, which is equals to 50 times 10 raised to power negative 6 coulombs. The second one we have there, the parameters we have there is electric field, which is equal to 50,000 Newton per coulombs. Now, the question is asking us, what mass should the charge have to remain suspended in air? So we are looking for the mass. We don't know it, so that's what we're looking for. We're looking for the mass. So, but remember that from electric field formula, we have it that E is equals to force over charge, which is force per unit charge. Now, let us try to make force the subject formula. So here, force will now be equals to electric field multiplied by charge. And you know from kinematics, from Newton's equation, that's Newton's first law, you know from Newton's law that force is equals to ma. Force is equals to what? Ma, that's mass times acceleration. So we are going to replace ma, we are going to replace F with ma. So here we now have ma is equals to E times Q. I hope that is taken. Then, since we are looking for mass, we are going to make mass the subject formula. Then by dividing through by acceleration, which is what? A. By dividing through by A. So this A cancels this A. So we now have it that M is equals to E times Q all over A. Now, let's go ahead and do what? And put our values. But remember that this A is equals to what? G, because it is directed to what? Upwards. So it's not going to be what? Acceleration due to gravity. So we replace this with G. Then our E is giving us 50,000. Then multiply by the charge, which is 50 times 10 raised to the power negative 6. Then divided by the constant acceleration due to gravity, which has a value of 10 meters per second square. So let's do that. 50,000 times 50 times 10 raised to the power negative 6 will give us 2.5. Then divided by 10 will give us 0.25 kilograms. So you see, the charge will have a mass of 0.25 to remain suspended above the ground. To remain was suspended in the air or above the ground. So this is our final answer. Okay, let's also proceed. Let's look at another example. Okay, an electron is released from rest. You see that? An electron is what? Is released from rest in a uniform electric field and accelerates to the east at the rate of 3 times 10 to the negative 6 meter per second square. What is the magnitude and direction of the electric field? What is the magnitude and direction of the electric field? Okay, let's go ahead and write out the parameter. We're talking about the electron. So let's write out the parameter. So the first parameter there we have is what? Is the acceleration. Is the acceleration. We have it as 3 times 10 raised to power negative 6 meter per second square. And we are looking at the magnitude of electric field. That means we are looking at E. That is what we are looking for. We don't know it. But remember, we are talking about here electron. We are talking about what? Electron. So let's look at the charge of electron. The charge of electron, which is what? QE. The charge is what? Negative 1.6 times 10 raised to power negative 19 coulombs. Please, it is a constant. The charge of electron is a constant. Also look at the mass of this electron. The mass is also what? Constant with a value 9.11 times 10 raised to power negative 31 kilogram. And we are looking for what? For the electric field. Then you ask yourself, what formula relates the mass of electron, the charge of electron, the electric field, and the acceleration? So we see that the formula is what? E equals to F over Q from the definition of electric field strength, force per unit charge. But we know from Newton's second law that F is equals to what? MA. So we have MA. Then all over Q. So which is the same thing as this M here now will be the mass of electron multiplied by the acceleration. Now here, this Q will now be what? The charge of the electron, because it is electron that is released from rest. So let's go ahead and put in our formula. So we have E to be equals to mass of electron is given as 9.11 times 10 raised to power negative 31, then multiply by the acceleration, or you can call it the linear acceleration. We have the value as 3 times 10 raised to power negative 6 is given, then divided by the charge of electron. The charge of electron is negative 1.6 times 10 to the power negative 19 coulombs. But here, the sign does not matter because we are looking at the magnitude of the electric field. So You may decide not to put the negative sign, it doesn't matter. So we have it as 1.6 times 10 to the power negative 19. So let's resolve it. So the answer will now be that E will now be, when you punch your calculator, it will give us 1.71 times 10 raised to power negative 17 Newton per coulomb. So this becomes our answer. Now, what about the direction? So remember, it says that an electron is released from rest in a uniform electric field and it accelerates what? Eastward. So since it is what? As accelerating what? Eastward this way at the rate of what? 3 times 10 to the negative 6 meter per second square. Then what is the direction of the electric field? So since this is a negative charge and here the force is going this way, that is to say that the electric field is going to do what? It's going to go in opposite direction. So which is what? West. Which is west. Is that understood now? So if you paid attention earlier, you will understand that it's the electric field will do what? We go in east direction. Okay, let's continue. Please, you are free to pause the video and look at it very well to understand. Okay, number 5 says a positive 20 microcoulomb point charge is placed at the origin. Is placed at where? At the origin. Calculate the magnitude and direction of the electric field created by the point charge at the following locations. Point Y, 4 meter, 0 meter. Point Z, 2 meter, 6 meter. So remember that we are going to represent this in a coordinate, in a Cartesian plane. We are going to draw our S and Y plane. So here, this is X. I hope you are aware. Y, this is what? Y. This is X. This is what? Y. So let us try and do that. So let's assume we have this. We can draw this. Good, we can draw this. Of course, you know that this is the positive Y axis, and this is the positive what? X axis. So we have this. And this is our origin. You are aware. As a physics student, you are aware this is our origin. Now, it says that a positive 20 microcoulomb point charge is placed at the origin. That means this point charge here, let us use the same color, is placed here. This is positive 20 microcoulomb charge is placed here at the origin. I hope that is taken. Okay. Now, let us try to get the scale. We can call here, we can call there, let's call it here 2. Let's go by 2s. 4, 6. So also here, let's use the same scale. 2, 4, 6. Good. Okay. Now it says a positive 20 microcoulomb point charge is placed at the origin. Calculate the magnitude and direction of the electric field created by the point charge at the following location. So that means we have a location what? Y. So we are going to first of all find what? Location Y. So how do we find location Y? So here we have 4 meter in, that is the S direction is what? Is 4 meter. Y direction is what? Is 0 meter. So we come to Y coordinates. We come to S coordinates, sorry, and locate our 4 meter. So here, this is our 4 meter. Here in S direction, this is what? Our 4 meter. This is our 4 meter in S direction. What about Y direction? Y direction is also what? Is also at this point because it's 0. It's also what? At this point. So at this point, we have our Y at this point, 4 meter, 0 meter. So this is the coordinate. Okay, let's locate our point Z. Where our point Z will be, our point Z will be where the S we have value 2 meter. Here, X here, we have value 2 meter. So let's use another color. X here we have what? Value. This X, the value is what? 2 meter. Because here, this is what S is here is what? Is 2 meter. Why the Y is 6 meters. So we go up, trace it up. So this is the Y at this point. So this is the Y at this point, and it is what? 6 meter. So here our Z will be here. So we have 2 meter. We have what? 6 meter. So it says calculate the magnitude and direction of the electric field created by the point charge at the following locations. Let's first of all calculate the magnitude of electric field at point Y. At point Y. Let's do that and see. Okay, at point Y, that is, can I say at, sorry, I'll use this. Okay, here, at point Y, the electric field E is equals to Q K over R squared. So, which is equals to, our K is constant 9 times 10 raised to power 9 multiplied by the charge. This is the charge here. 20 times 10 raised to power negative 6. We are converting it. So this is equals to 20 times 10 raised to power negative 6 coulombs. And also, this is in meter, okay? Then divided. Here, the distance is what? The distance is 4. So 4 square. Now let's resolve that. 9 times 10 to the power 9 multiplied by 20 times 10 to the power negative 6 divided by 4 raised to power 2. So when we resolve that, we are going to have okay, 11,250 Newton per coulomb square. That is the electric field at point Y. Now, the electric field at point Y, where will be the direction? What about the direction? So the direction is going to be, the direction is going to be what? Is going to be what? East. Is going to be what? East. Because this is the point charge Q and it is positive. So the field will go in this direction. So which is what? In eastward direction. I hope that is well taken. Okay. Now let's go ahead and look at the magnitude of the electric field at this point, Z. Let's take a look at that. Okay, I am going to clean up this. Okay. Now, if you see this now, here, this is Z. At this point, Z is what? 2 meter and 6 meter. That is 2 meter is S distance in S direction. While the 6 meter is what? Distance in Y direction. Now, how do we resolve the magnitude of the electric field at this point? Now, if you take a look at this diagram, you will see that it's a right angle triangle. See that now? It's a right angle what? Triangle. So let's write it out. So it's going to be something like this. It's going to be something like this. Is a right angle what? Triangle. So here, this is 6 meter. You agree with me? Why this is what? 2 meter. So we are going to get our R. And for us to do that, we use Pythagoras theorem. And it states that R is equals to square root of A square plus B square. So let's put in our value. R will be equals to square root of 2 square plus 6 square. So when you do that, our R will be equal to square root of 4 plus 30. Okay. All right, so we have square root of 40, root square, square root of 40. So our R will be equals to square root of 40. There's a square root of 40. We have it as 6.32. Okay, so meter. So we have gotten a distance. Good. So let's now look at the magnitude. Let's solve for the magnitude. Then that is okay. For position Z, so from Coulomb's, from electric field formula, E equals to KQ over R square. So we now have it as K is constant, 9 times 10 to the power 9, then multiply by the charge. The charge is the same thing, which is 20 times 10 raised to the power negative 6. So this is the charge here. Then divided by The distance is 6.32 all squared. All squared. So when you do that, okay, so you will have E will now be equals to 9 times 10 to the power 9 multiplied by 20 times 10 to the power negative 6 will give us 180,000, then divided by 6.32 raised to power 2 will give us 39.94. So our E, electric field at point Z, will be equals to 4506.8 Newton per coulomb square. Okay, per coulomb square. Okay, what will be the direction? The direction will be, what will not be the direction? Here, the direction will be here, the direction will be what? North of what? East. North of what? East. So you see here, direction will be what? North of east. Direction will be northeast. Will be northeast. So we can also go ahead to calculate it. So go ahead. Okay, let's bring back our triangle and see how we can do that. Let's bring back our triangle. Remember, this is our triangle we had. This is our triangle. And this is 6 meter. And this is what? 2 meter. So we're going to look at this angle here, theta, since it's a right angle triangle. And since it's a right angle triangle, we're going to use what? Tan. So we have that our tan theta is equals to opposite over adjacent. So 6 is the one that is opposite to the angle. The one that is opposite to the angle. So it's not going to be tan theta is going to be 6 over 2. So which is going to give us 3. Then let's look at the angle theta. It's now equals to tan inverse of 3. We have it as 71.57 degree. So it's not going to be, the direction is not going to be what? 71.57 degree north of east. North of what? East. Okay, I hope that is clear enough. So you are free to pause the video and go through it. And please don't forget to put a comment so that I can clarify you if you're having any doubt. Okay, let's go ahead to the next question. Okay. An electron initially at rest is placed in an electric field of 2 times 10 raised to the power 4 Newton per coulombs directed to the west. The distance between the plates is 1 cm. What is the acceleration of the electron due to the electric field? What will be the speed of the electron after it leaves the hole? Okay, let's look at that. Let's just make a quick sketch of that. So this we have this. Okay, we have this as our electron. We have this electron. We have this as our electron, and we have this. We have this as our, that's positive charge. So we have positive charge here. Sorry, I think I'm going to use red on that. So we have positive charge here. Have positive charge here. So here we have our electron here is trying to leave. So good, good. Now remember that the electric field will be directed towards this negative charge. I hope you're aware of that. And since the electric field is directed towards this negative charge, so the force will be in opposite direction. I hope you know that because we have positive and what? Negative. So the force will not be in this direction. Okay, I think let me use another color. The force will not be in this direction. The force will be in this direction. So this is the force. Why this is the electric field. This is the electric field. Okay. Now let's look at for A. And here the distance, sorry, let's take the distance here. The distance is what? 1 cm. So this 1 cm is equals to, okay, 1 cm is equals to 1 divided by 100. So we have 0.01. So here will be 0.01 meter. Okay. Now let's look for A. A says, what is the acceleration of the electron due to the electric field? What is the acceleration of the electron due to the electric field? Now, what do? We state the formula for what? For electric field. E is equals to F over Q. But we know that F also can be equals to electric field multiplied by the charge. And F from Newton's second law is equals to ma, which is equals to E multiplied by Q. Remember, we're looking for the acceleration. So we make A the subject formula. So A here will now be equals to electric field multiplied by the charge Q divided by what? The mass of what? Electron. So this is what? The mass of electron, right? Let's go ahead and put in the value. So which is equals to electric field is what? 2 times 10 raised to power. Okay, sorry. Let's use the color so it makes sense. Okay, is equals to 2 times 10 raised to power 4, then multiply by the charge. Multiply by the charge. Which charge are we talking about? We're talking about what? Charge of what? Electron. Charge of what? Electron, which has a value 1.6 times 10 raised to power negative what? 19 coulombs. So divided by the mass of electron. The mass of electron is 9.11 times 10 raised to power negative 31 kilogram. So when we resolve that, we are going to have 3 point, okay, sorry. We are going to have 3.5. We have 3.51 times 10 raised to power 15 meter per second square, because the unit of acceleration is meter per second square. Okay, now let's go ahead and look at part B. Part B said, what will be the speed of the electron after it leaves the hole? What will be the speed of the electron after it leaves the hole? So from kinematics, we have equations for linearly accelerated what? Motion. So we are going to use one of the equations there. V square is equals to u square plus 2ax. Here we are looking for v. We know our initial speed, which is 0, because electron initially at rest, meaning that the initial speed is what? 0. And we have our acceleration and we have our distance. So here, our v will now be equals to square root of u square plus 2as. So let's go ahead and put in the values. Our initial speed or velocity is equals to 0 because it is at rest. Then plus 2 multiplied by our acceleration here. This is our acceleration. This is our acceleration, which is 3.51 times 10 raised to power 15, then multiplied by our distance here, which is here. This is our distance, 0.01 meter. This is our distance. So 0.01. So let's resolve that. So we have it as is equals, we have it as square root of 2 times 3.51 times 10 to the power negative times 10 to the power 15 multiplied by 0.01. So we have it as 7.02 times 10 raised to power 15. Then when we take square root of that, we are going to have 8.38 times 10 raised to power 6 meter per second, because the unit of speed or velocity is equals to meter per seconds. So we have come to the end of today's class. Please don't forget to subscribe. Please subscribe and share this video with others so that they can learn. If you have any question related pertaining to this electric field, feel free to drop it on the comment section and I will attend to it. Have a lovely day.